Okay. I hope I'm okay. It can be heard. Perfect. Yeah, since we are getting to late hours here locally, I'll move without ado. Okay. Yeah. Okay. Perfect. Yes. I will. Yeah. Given the time and also the very intensive talks we already had today, I thought to just give a bit of overview of why composite particles might be interesting. And I would like to talk also about something I usually skip, and that is why these considerations, even if we completely are not interested in any of the fundamental big questions, they might be interesting from the point of view of how they might affect or show up in high precision experiments that might be coming on the horizon. And so I joined University of Stockholm only in February this year. We are starting up a group, so already have 2 PhD students, Jermaine and Jerzy, and Evan is visiting here at the end of the year from Australia, and we should be expanding to also a postdoc later in February. So yeah, this so it's a nice opportunity for me to have the chance to speak in a new place still for me. So the research that I typically am interested in, I think I can at least for myself break into some 4 different types of topics. So questions about new phenomena and testing the theory and the interplay between quantum mechanics and general relativity. So this is something I'll talk a little more today. The questions about the notion of temporal and causal order, again, and the interface between quantum physics, relativity, and general relativity. Have some interest also in alternative theories, mostly from the perspective of how different desiderata between models actually, whether they are actually embedded in the theories, and how such models can be tested. And sometimes it turns out that the direct test of the principles behind the model might be very difficult, but once the model is mathematically formulated, there might be ways to test it that are much more achievable with the experiments. Again, I'll not talk about this today. And finally, something maybe has been talked more about today, and also by my collaborators from Waterloo, and that is looking at various aspects of quantum field theory in classical and quantum curved spacetimes. And so now, I think here probably there is not much motivation needed to talk about quantum mechanics and gravity, because many people have already kind of committed to that side of research. But I think it's worth reminding that while we have a lot of different and very exciting theoretical frameworks, and there are different ways that one can explore and even formulate fundamental questions in terms of experiments, what we had verified, I mean, we in terms of community, when it comes to joint quantum and gravitational effects, are only effects where gravity shows up as a non-relativistic Newtonian force. And Igor has mentioned already cow experiments, and that's where you can measure relative phase due to difference in the Newtonian potential. Starting from 70s, it's something really really noteworthy is that it was the first time in 2017 where such atomic experiments that probe phase shift due to gravitational interaction. It was for the first time 2017 that in order to describe this phase shift, one needed to go beyond homogeneous Newtonian gravity. So up till that time, it was not only Newtonian gravity, but essentially constant acceleration. So that's, I think that it really shows how big gap there is between experiments and the aspiration to understand everything that is to know about the foundations of the quantum and general relativistic world and all the concepts that, of course, we will study. But I think that is that is something that can motivate research into the regime where it, theoretically one might think everything is already known, but there might be still new effects lurking that could be useful to help bridge the gap at least a little bit. The second class of such experiments that I find particularly nice are experiments where you trap neutrons in the gravitational potential well above some reflecting surface, so you create a wedge-shaped potential. And again, that's, I guess, maybe nice just for theories because you can get analytical solutions, but you can also do experiments. So I think probably that's this kind of unique situation where you can find it both practical and also describable. Here you have a picture of the setup, this gray aluminum box, and I believe that this part here somewhere, or maybe here, is where the neutrons are propagating to where they equilibrate. And of course, there is a fundamental framework, or at least the one that we currently can put a finger on as the most fundamental from fully completed ones, field theory, quantum field theory in curved spacetime. But that's exactly where, in some sense, the exploration starts, because the natural phenomena that are inherently captured by this framework are typically accessible or show up themselves at high energies. So in terms of bridging the gap between experiments and the theory, this doesn't make it obviously simpler. So there is a different strategy that one can pursue, and that is what I would talk a little bit more about. And so this strategy relies on understanding that we actually do measure relativistic phenomena that are not associated with typical high energy or fast velocities, and this is when we employ clocks to measure time dilation on redshifts. So already in 2010, such experiments with atomic clocks could measure gravitational redshift at the scale of 33 centimeters. So you have these atomic clock setups, which means atoms trapped in some optical potential, and order of 10 centimeter separation between such setups was sufficient to produce enough gravitational redshift between internal energies and therefore frequencies of these clocks to be measurable. And likewise, moving in some sense, trapping potential for one such clock led to detectable special relativistic time dilation. So this order of 10 meter per second. So this is a human scale. So this is certainly not some high velocity. So let's say after taking a course in special or general relativity, if we ask if 30 centimeter is a relativistic scale in gravitational field, or if this velocity of, say, trotting or maybe fast walking, is it relativistic speed, we would say no, but simply because we are used to very lousy clocks. The answer is yes, of course. We just need a clock that is precise, can measure time to such and such precision. So essentially, if we had arbitrary precise clock, there would be no regime in which we could apply non-relativistic physics. And since these systems are getting now so precise that you can measure time dilation across millimeter scales, it's worth to explore a little more a theory that can describe such systems that are used in these setups inherently, so atoms that are both described by quantum mechanics, and where we can include directly in the dynamics of these systems the relevant relativistic corrections that could be observed at low energies. And that's exactly the topic of composite particles in the context of general relativity. And so there are, of course, various ways you can start, because we are here only after an effective model. So there will be many different starting points that in the end lead to the same effective theory. I mean, in the end, this is if you only want to recover the lowest order relativistic corrections that come from the redshift type effects. It will be more clear, I guess, as I go. So here are just some examples of you starting with something like a bunch of electromagnetically interacting particles, or some composite field in space-time described by some metric. So typically, actually, I mean, all these formulas actually only hold if you have static, symmetric, metric. And depending on the set of slides, I do mention it or not. So let me say it right now. And so in each of these models, you can take steps to recover the regime where you have one particle sector, where for the field where you introduce a relative coordinates for the rest center of energy frame, and there is a regime where it approximately can be done in relative coordinates, and you recover effective description that looks like so, where you essentially have a dispersion relation like you would naturally write down for a relativistic particle, but you have internal energy that essentially presents itself as a rest mass that is given by the operator. So that's exactly the energy of this composite system in its rest frame. And so you can call it M or you can call it H. That's really just the difference in the symbols you like to use. In effective models, like the one would have behind anything like an atom that we'll think of throughout this talk. One should think of this operator is essentially, it's a highly complex system, and it has nuclear energy scales and electronic energy scales, but essentially you will only access very few of these internal energy levels, and in this talk only 2. And so the lower one you can call M, so the ground state of your Hamiltonian, you can call M, and everything else you can define as your internal Hamiltonian, essentially Hamiltonian that drives the dynamics relative to the center of mass. And when you include this split and look at the low energy expansion of this Hamiltonian, you find the fully non-relativistic dynamics of the center of mass, just a non-relativistic particle, some Newtonian potential, and then you find correction terms that couple center of mass and the internal degrees of freedom. And so these are the ones interesting from the point of view of trying to look at the time dilation or redshift effects, because these are exactly those that capture these specific phenomena. Now there are, of course, other terms that if one would like to have just a Taylor expansion, order 1 over c squared, but they will only contain center of mass terms. And in the regime, like cold atoms in some trap, one can verify that essentially there is a regime in which you can neglect such terms, where you cannot neglect those that couple the internal and the center of mass. So this becomes really particularly elegant, because if you fold it back, essentially you will find that you effectively obtain a system that looks like a non-relativistic particle with just mass energy included. And so these terms are exactly those that incorporate a redshift or time dilation effect. So phi stands for the gravitational field, and you can easily see if the internal Hamiltonian has some frequency omega. This term gives you gravitational redshift of this internal frequency. And for some semi-classical motion, if you recall P on M to this order will give you velocity, then you get the lowest order correction that comes from the Lorentz factor due to the kinetic motion. Now, in experiments like those with atomic clocks, one of course has to describe fully in terms of quantum mechanics the internal degrees of freedom. However, the center of mass is typically considered classically or semi-classically. You consider the atoms are trapped somewhere. You are not giving a full quantized description of both, but that's exactly what would be the interest for this talk. And so Igor already mentioned that if you have some system like this, where you have a particle that has internal states that can evolve in time, you can think of it as a quantum clock. And instead of having 2 sets of clocks at different heights, for example, you can have one at superposition of height, and then you get, instead of typical interference fringes with just some phase shift that depends on gravity, you get some modulation. And this modulation is an effect that will not be there in a non-relativistic theory with a quantum clock, and of course would not be there if you have a relativistic classical theory. So if you've had classical relativistic particles in the interferometer, well, they will also not show interference fringes. So in that sense, this is an example of an effect that combines both. And there are some prospects for experiments. Now, in the remaining minutes, I would like to highlight some other incarnations of these composite particles. So far, I built all the intuition around those particles that can be seen as idealized quantum clocks. They can have quantized center of mass and quantized internal states. But because essentially time dilation and mass energy equivalence, they are just two different descriptions of the same physics. These particles inherently are also they have different states associated with different mass, and in that sense they also allow to study equivalence principle and in general theories with quantized mass from this perspective are put on firm footing. You can couple them to some external field, and we heard already today Evan talking about a model that arises from that, where you have a quantized center of mass dynamics. You couple also to the field, so this can be studied in this context. And you can also couple them to some external bath and have a quantum thermometer. In the remaining 3 minutes, probably, perfect. I would like to highlight one aspect that comes kind of from the side, but it turns out of interest to people that are planning to make experiments using, for example, atomic clocks more and more precise. And so to lowest order, obviously, such any trap particle you can describe with some potential. So we'll use to ping pong the pun. This is the ADS of the quantum mechanics, the harmonic oscillator. You will have to watch a talk of Bosenberg to understand the reference. So we'll be looking at composite particle subject to gravitational potential and harmonic potential. So this is an exercise essentially. Everything about this can be solved exactly on just a few pages. And so typically when we think of some harmonic trap and the qubit inside, we would think, well, we'll have some states associated with the qubit and some states associated with the trap, and that's it. And while this is very simple, it's actually doesn't give you exactly that picture, and you can very easily see why it's the case when you just formally write down the normal mode operators here. And of course, the fact that you have a spectrum here, I mean, your mask has some spectrum, but if you just recall that the solutions for any trap system essentially depend on the mass, you'll recover that your modes depend on the mass. And what it gives you essentially is, so, well, you can find description of these modes, but probably the more interesting thing is that if you look at the spectrum and the eigenstates, so the eigenstates are correlated, so you don't have a separate tensor product, so the eigenbasis is not tensor product of the eigenbasis, and the energy spectrum acquires some corrections. So interestingly, one of such corrections is known to the quantum clock community, and that's called the time dilation shift. And the interpretation here is if you have an atom with some in some thermal state in a trap, it has some kinetic energy. So if it was a classical particle, it would be moving around with some velocity, and there will be some Doppler shift. Now, if this is a thermal state, there is a spread of velocity, so you get some spread in the frequency of your atom. So with this kind of back of the envelope, they can calculate from knowing the temperature of the atom and parameters like mass. They can get the order of this shift. And here, this is something that with even this very simple model, you can just very easily derive. So this is the same effect, and this has been seen, of course, in experiments. Then there is this additional shift. I mean, additional just in a sense that it hasn't been measured yet, but apparently people in this community have been discussing whether or not it should be there. So yeah, at least within this setup, it should be there a shift that simply comes from the fact that if you have some fixed trap stiffness such that both states see the same potential, then the center of this potential is different for different masses. And this shift then also corresponds to the shift in the spectrum. And there is some absolute minimum to this shift that happens for some very low trap frequencies. I think I'm now at the end of my time, so perhaps I'll just move on to conclusion. I had some bonus topic, but I'll skip it, and I'll just move to my conclusions. I'll move back to the first slide. Some CTC. I have some trouble finding, maybe. In summary, I think we probably don't even need the summary, but I think there is, apart from fundamental questions that I don't want to neglect, I just thought to fill in the niche, but apart from fundamental questions, one can also ask questions about how we can capitalize on the kind of theories that we have been developing to help find some experimentally friendly way to look at the regime beyond the one that has been tested so far. And I think maybe with this I'll end. If there are any questions, I'll be happy to take them. Thank you.
Have some time for a couple of questions if you want. Yeah, go on.
So the effect of gravitational potential in the center of mass motion, you said that was not relevant for the time dilation?
For the clock experiment?
Yes.
So this, the tighter is the trap, the smaller this effect is. I think I maybe had a number. I think from memory it would be a shift, like a relative. So this effect would introduce a relative frequency shift at 10 to minus 26. That's not something that can be seen currently, and so whether it's there or not cannot be said. But 10 to minus 19 is something that would be what kind of determines the minimum frequency shift in some of the experiments, like trap times.
Is there a qualitative way of seeing why the scales are so different for the two contributions?
Well, so one is essentially, okay, in a sense, I think yes, because one, so if you switch off gravity completely, then you have only one, and that comes from special relativity. That comes from the fact that even if I don't have gravity, but I have harmonic oscillator with varying mass, this will give you some additional effects on the spectrum. And then additionally, you have a constant force. And so they are these two different effects. So one is essentially that you just have a effectively interaction because of the kinetic term between internal degree of freedom and the center of mass. And then the other one is an additional force that shifts the equilibrium states.
Yeah. In the cow experiment, so the fluctuations of the phase, would it tell something interesting about, or are these so there is this phase by Newtonian potential, but are there fluctuations around it that are measurable, and would that tell anything about the quantum nature of gravity, like fluctuations in LIGO kind of scenarios, or would it?
Okay.
It's not.
Okay, I can maybe I can address a cow experiment, because maybe that's something where I feel more more confident. I understood the question. So. Yeah, nominally you could take a neutron. So if you, people studied it, like we didn't really start it. So you can take a neutron in, I think the most complete description, at least I've seen already in papers probably from 80s or 90s at least, actually from Japanese authors. I think Matsumoto was among them. They would, you can study how such an experiment would look when you describe a neutron via Dirac equation in curved spacetime, and you find some additional contributions to the phase. Now, from our perspective, it will be interesting to add some additional external field, so you can use the spin of the neutron, and this can help to give some additional handle and introduce them something more akin to the clock. And with Germain, we look at something like this in the context of these neutrons that are trapped above the table. So there also you can add some additional field and ask, how big the additional relativistic effects would there be? Because to lowest order, even though we have a spin, it gives something similar to the mass effect. I think we need a pretty solid magnetic fields. Something like blowing up the laboratory would be kind of just a bit short of, but it just was more to see qualitative. But with the joking aside, if you actually look from the point of view of metrology, Germain found that actually that could be ways to find more precise ways of measuring than just kind of waiting where the neutron comes out, and that's something that could be explored to kind of ask this question. Maybe what exactly one would need to measure, so to see those corrections rather than just doing all the experiments and looking for corrections, there might be different ways to make measurements that would be more sensitive to those effects.
Okay.
Yeah.
So we can thank Magdalena.
Yep. Thank you.